So we've talked about the relative age of fossils and how the ones on the lower are going to be older than the ones that are on top. Now, the fossils usually layer in areas where the time was formed. So we can actually look at a layer that was formed, say, here, and if the fossils in here are similar to fossils that are found around somewhere else around the world, we can assume that those layers are going to be roughly the same age, relatively. Now you can see that because we can look at how old things are, the older the fossil is, we can assume that the farther down it is, the older it can be. So if we can look at the evolution of a horse, we can start seeing that 40 million years ago, roughly, we can see that this animal had multiple toes on one foot, and it was also much smaller. 25 million years ago, you can see that those bones started to fuse and were three. We can see that down here, this is starting to come into one, to have one hoof and a couple of dew claws off of there, similar to how you would see, similar to a cow-ish. And it's also showing the tooth as well. Also, it's getting a little larger. 7 million years ago, we're down to having one hoof. We're also seeing that it's going to be a little larger, and then now we actually have the equine right there. We can see the similarities from the front leg, or the legs, and the teeth that are through there. So you can see how things have progressed, and based off the evidence that we have, this is where we end up with the modern day horse. Now, radiometric dating is a little different. Radiometric dating gives us an actual year as to how old it is. If we were to discuss your actual age, is going to be found in a year. You guys are roughly 15, 16 years old. That is going to be more of a specific date. Radiometric dating gives us that. So, some elements, such as uranium, undergo radioactive decay. That is the term that is going to make this whole thing possible, because they're going from uranium down to another element. In this case, I believe uranium decays down to lead. Now, they have what are called a half-life, which means they decay at a constant rate over time, but they decay to half as much as there once was. So the amount of radioactive elements remaining in a rock can help scientists determine how much time has elapsed since the rock was formed and cooled. So since it was initially formed and we ended up with that rock, over time we can see how old it is. For long-term dating, we use uranium as it decays to lead, and potassium as it decays to argon. These are going to be ones that are millions of years old. They are old, old, old. One of the ones that we're going to use for organisms is actually going to be carbon. Carbon-14 is an isotope that can be used for dating in more recent fossils and artifacts. Carbon-14 breaks down and starts to lose neutrons, breaks down to carbon-12. So we see carbon-14 is radioactive, meaning that it is going to actually lose energy, lose neutrons, and it decays at a known rate. It is roughly 5,000 years is its half-life. So if we can compare the ratio of carbon-12 to carbon-14, we can get a pretty good age of how old a fossil is. So for example, when it starts out, it's going to have 100% carbon-14. The half-life is going to be 5,000 years. If we find a fossil that is 50-50, we can assume that that fossil is roughly 5,000 years old. 75-25, it's going to be 10,000 years old, and so on and so forth. So we can see that through this, we can get a good idea of how old these fossils are. Here's our organism, breaks down, we have it figured out to what we have there. So, until next time.